Can you run a 27 billion parameter model on a modern iPhone? Prism ML just showed this is possible. And they did it at a useful speed of 11 tokens per second on iPhone 17 Pro, which is kind of crazy. So in this video, I'm going to show you how exactly they were able to achieve this. Because the interesting thing is that they were able to preserve the quality of the model. Okay, so how exactly did they do it? The whole magic is in the name Bonsai. And the idea is that you can create miniature version of trees of full size without losing their shape or structure. Now, in this case, they were able to bring down 54 gigabytes from full precision to 3.9 gigabytes. Now, the first thing that comes to mind is quantization, and that's exactly what they did, but with a twist. Okay, so most of the smaller models are these days trained in full quantization, say floating point 16-bit. This means you have a fine grid to represent different numbers. But that also means you will need a lot of memory in order to accommodate the weights. So people quantize it down to 8-bit or 4-bit. That gives you coarser grids with rounding errors. But the result is that you need fewer bits in order to store the weights of the model. And this is what enables a lot of companies to create smaller versions of the model, but they lose precision. Now, this is a very useful art to remember. So if you have a 7 billion parameter model in 16-bit precision, you need about 54 gigabytes. If you bring it down to 4-bit, you will need 18 gigabytes. Now, if you use ternary representation, which means you use 3 different states, -1, 0, and 1, then you will need about 5.9 gigabytes. But then there is this 1-bit Bonsai, where you basically have 2 different states, -1, +1, and you need a total of 1.125 bits in order to represent that. But the storage need is going to be 3.9 gigabytes now. Now, the problem with quantization is that you lose precision or performance in the model. Now, so far, people have tried to run smaller 2 billion, 4 billion model on phones, but their intelligence is limited. You cannot run a full 27 billion parameter model, even in 4-bit quantized, because that basically goes beyond what the current phones give you in terms of memories. But if you use this 1-bit Bonsai representation, you actually have enough headroom not only to run the model, but also use it with a usable context window. So here we are talking about real useful work that you can do on the phone. Okay, now you can theoretically quantize the model, but you pay with the quality. So the naive way was to do quantization post-training. Just round an already trained model, and each weight's error is going to look tiny. But those errors actually compound through dozens of layers, each amplifying the last one, until the output drifts off the rails. This is compounding error. At 2 or 1 bit, the grid gets so coarse, the learned structure completely collapses. And as a result, for highly quantized models, you see a lot of repetition, gibberish, a stream of exclamation marks, and things like that. Now, by that logic, a genuinely useful 1-bit model should be flat out impossible, right? Now, in theory, if you simply do naive quantization, that is exactly what you're going to get. But they did something different. Okay, before I explain the technique, you actually need to give open source credit because they're building on top of what other people have done. So first, we need to look at llama.cpp and the GGUF K-quantized, which is a mixed precision where you spend extra bits on the fragile layers and using the rest of the network. Then came the GPTQ, made it calibration-aware. So essentially, the idea is that you quantize while watching sample data. So it rounds where it hurts real output the least. That's basically calibration-aware quantization. Then there was AWQ, which went activation-aware. So the idea here was that find the weights that fire hardest during inference and guard those specifically. Now, if you stack all of these tricks together, the quality curve holds beautifully for quantization all the way up to 4 bits, which is kind of incredible. But if you try to quantize it further to say 2-bit or 1-bit, the degradation is catastrophic. Now, so far, we have only been talking about post-training quantization, but the bigger idea is quantization-aware training. Instead of rounding after the fact, you train the model to expect low bits. So it keeps shadow full precision weights, but practices rounding on every forward pass, so it learns weight that survive the crush. Now, a good example of this was BitNet. Really proved this at the extreme. They showed that ternary weights, if trained from scratch, can actually hold up the effect of quantization. Now, the beauty is that you can add a group-wise scaling from earlier that we saw to preserve the dynamic range. Then they essentially distilled the full 27-bit teacher into a tiny student. Now, with these approaches together, they were able to preserve 90% of the quality of the bigger 27 billion model. So as you saw, we are actually building on open source work, and here's how exactly did they do it. So they actually started with a base Qwen 3.6 27 billion model in full size. Then they created a compressed derivative of it. Now, if you think about a transformer as 4 zones, embeddings, attention, the ML layers, and then the LM head picking each token. So a typical GGF quantize is going to crush most zones, but leave the LM head in high precision, which is essentially a little escape hatch that is going to protect the quality. Now, in case of the on-site quantization, they quantize everything end to end, including the LM head that is on top. Everything is quantized down to 1 bit. Okay, it ships in 2 different flavors. One is ternary and the other one is 1 bit. The ternary is 1.71 bits and the total required storage is going to be around 6 gigabytes. The other one is a single bit with 3.9 gigabyte, which is great for phones. Now, in terms of the quality, the ternary preserve about 97% of the base, that is the 2.27 billion model. And for 1 bit, it still preserves up to 90% of the base, right? Which is kind of incredible in terms of the performance that it still keeps. But here's the most interesting part. The original 27 billion model is multimodal, and it stays full multimodal agent. You have a 4-bit vision tower, which is going to be around half a gigabyte, which you can use for reading screenshot documents and even your camera. And it carries about 262,000 token context window, which is more than enough for a lot of applications. Now, you can even use speculative decoding with it. They actually have implemented DGX Spark based drafter. So that drafting model guesses several tokens ahead and the big model verifies in 1 pass. If you are interested in the topic, I have a dedicated video on that. Make sure to watch it. Now, with all this, you can run this model on a modern iPhone, which is crazy to think about. Okay, so we talked about speculative decoding. They are using DGX Spark, which means it's going to give you much better latency. And in fact, you get about twice the speed with this model compared to the base model without speculative decoding enabled. Is a substantial improvement if you need high throughput and lower latency. And it's essentially free speed. The drafter only proposes, the big model still verifies every token. So the output is almost identical. This is new work from DeepSeek, which is already making its way to production load LLMs. So with all this quantization, does the intelligence actually survive? So here are the benchmarks from Prism ML compared to the original Qwen 27B. And if you look at it, depending on the task, it actually preserves the performance really nicely. Now, the biggest drop is specifically for tool calling, where you see substantial degradation for the 1-bit Bonsai model. But for something like math or coding, it still preserves most of the performance. So you could essentially use this as a chat model for information retrieval. However, for agentic tasks on an iPhone, it is probably not a good option. Okay, so when it comes to intelligence, Prism ML introduced this concept of intelligence density or capability per gigabyte, where they show that for this 1-bit Bonsai model, it scores 0.53 per gigabyte, which is over 10 times full precision and about 2.7 times that of the best low bit precision. Now, it's fast enough that you can actually run it as a usable speed on iPhone or all the way up to an RTX 5090. And with this research, they really wanted to show that it's possible to preserve capability per gigabyte rather than just the raw intelligence. But keep in mind, this density is not the same as quality. Okay, so I have it running on my M2 Max with 96 gigabytes of VRAM. It's more than enough to run a model of 27 billion parameter. However, right now I am running it in 1-bit precision, and I wanted to show you what the actual speed kind of looks like. So we're going to ask it to explain quantization in 3 bullet points. Now, keep in mind, 27 billion model is a thinking model or reasoning model, so it's still preserve the reasoning capability, and the speed of generation that I am getting is about 29 to 30 tokens per second, right? Right now it's generating the response for us. It's pretty fast. It's a reasonable speed of 28 tokens per second. So now the answer that it generated was discretization of continuous values, efficiency and compression, and then it talks about precision trade-offs. Okay, the first part is actually reasoning tokens. So you can see that the reasoning ended here. Because during the reasoning or the chain of thought, it actually goes through the different constraints. So it looks at 3 bullet points. It's yes, explain quantization, clear and concise, no extra fluff, right? And then it actually gives us the answer. So it seems like there is some problem in the way rendering was implemented on my end. Now, next I'm going to ask it something more serious. So right now I'm asking it to create a simple encyclopedia of the first 25 legendary Pokemon, include their type, lore, snippet, and images. Now let's see how much knowledge it actually has. So again, we're going to look at speed of generation. Again, we're getting around 30 tokens per second. Okay, so it seems like it's stuck in a loop. So you couldn't probably use it for a much harder task because it's just repeating the same thing again and again. So with this quantization, it definitely seemed to have that looping effect when the task gets harder, which is really interesting. So I'll have to stop it here. Now, I'm going to run some more experiments to make sure that I represent a real picture of how the performance actually looks like. But I like the idea of these companies experimenting with novel architecture and novel techniques, because this is the only way we will be able to push the boundary of local AI. Anyways, I hope you found this video useful. Thanks for watching, and as always, see you in the next one.